Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's video we're going to touch base a little bit with some fundamental physical ideas, introducing things having to do with motion, time, and change. So we want to be on the same page with respect to some basic orientation and terminology. Okay, so in physics, of course, motion of particles and more generally objects is important. Historically, in astronomy, the motion of the sun, the moon, the planets, and the night sky was crucially important to understand this picture that we now recognize as the Earth revolving around the sun, rotating on its axis, which is leading towards this plane, a moon circling around the Earth, the axis of precession of the Earth actually also making a motion. So quite a complicated juxtaposition of motions there. In warfare, the idea of a projectile, describing what happens to a cannonball, is an important example. And then in engineering, all kinds of linkages. For example, this one generates the Leibniz skate. You have two fixed points and you have some bars, 3 bars actually, fixed to these 2 points here with revolving joints here and here. And then as these bars move around their respective centers, the midpoint of this side will trace out a Leibniz skate. It's an example of a 3-bar linkage, an example of an industrial or engineering kind of apparatus. But when we're talking about motion, we're not just talking about physical things. We can also talk about more abstract things, in particular economic things. For example, we can think about the motion of a price graph with respect to time. How does the price of houses, for example, vary according to time? It's also a kind of motion. So we want to talk about all of these things in a kind of a language that allows us to apply calculus ideas to a broad variety of different situations. So when we're talking about motion, and talking about change, usually time is a common important feature. And most of the time, time will be represented for us with the letter t. But not always will t denote time, but often it will. So for example, here is a cannonball, the trajectory of a cannonball, and we know, following Galileo, that this is basically a parabolic arc. But people did not always know that. And in earlier books on the subject, they had ideas like that the ball would go up to a certain point and then it would almost drop vertically down after it reached its maximum extent. So this was not an obvious understanding that something like this happens. And moreover, we're interested in where it is at given times. So we don't want just the trajectory, but we'd also like to know where things are on that trajectory at given times. Another important situation like that is the example of a planet or a comet going around the sun. So here we have something like this. This is an elliptical path that we now know is the general story, with the sun at the focus according to one of Kepler's laws. And the motion of a planet or a comet along this trajectory will not be uniform. It will be moving faster as it gets closer to the sun, and then it will slow down as it gets further away, and the force of the sun is less. So that's represented here by these increments. So these are sort of equally spaced time observations, measurements if you like, that illustrate the fact that the position and the speed of the particle is not uniform. So a general question that's very important in physics is, where is an object at a given time t? Mathematically, we'd like to express the position p equals p of t as a function of t. So define this relationship between the time and the position of an object or a particle, or maybe even a system. So this is a fundamental aspiration of physics, is to try to understand how particles of systems evolve with time, actually rather explicitly. So change, of course, is very important in calculus, and in calculus we have a letter or a symbol that denotes change, and that's the Greek letter delta, the capital delta that looks like a triangle. So that symbol will often denote change. And typically the way we might use it is if we write delta of z, we're talking about the change in z as we go from one value of z to another. often in terms of an initial value and a final value. And the change in z is the difference between the final value and the initial value. Final value minus initial value. So for example, suppose you've just got a job a year ago, and on your first anniversary, your income is 65K. And then when you get to the 5-year period, your income is 81K. So it's changed. Okay, so the change in income would be the 81 minus the 65, which is 16K. The change in time, accordingly, would be the difference between 5 and 1, which is 4. And having these two things, being able to compare the change in the quantity that we're interested in, comparing that to the change in time that's elapsed, gives us the important idea of the rate of change of a quantity with respect to time. So the rate of change of the income here with respect to time is the ratio of the change in income to the change in time. 16K is the change in the income, 4 years is the change in time, so the rate of change of income with respect to time is 16K over 4 years, or 4K per year. That's the rate at which your income is changing. It's increasing on average by $4,000 a year during this interval between year 1 and year 5. Now, an important special case of that is when we're considering a moving particle, and we're interested in the rate of change of the position with respect to time. That's called the velocity. So the velocity of the particle is the change in position over the change in time. And it's often described as an average velocity because we're taking the average over a given fixed interval of time. From time equals this value to time equals this value, the average velocity in that interval is the change in position over the change in time. So if we're moving around in 2 dimensions, it's often nice to illustrate these things with a particle moving in 2 dimensions because there's a bit more room to see what's going on. And also the vector aspect of the velocity becomes clearer. Okay, so we have a particle moving in the plane, and at time t equals 0, we're told it's at p of 0, which is 3, 1 right there. And a little bit later, at t equals 5, we're told that p of 5 is 8 minus 2, which is that point there. Okay, so what's the average velocity in this interval? Well, it's the change in position over the change in time, and this is a vector quantity. So we're talking about p5 minus p0. I remind you that the difference between 2 affine points is a vector. So it really helps for us to have that concept right here. The difference of points is a vector, so this numerator here is automatically a vector. And the change in time is 5 minus 0. So here's the point p of 5, and here's the point p of 0, and we have to take the difference and divide by 5. And what are we going to get? Well, we're going to get a vector, which is 5 minus 3. All of that divided by 5. So we're going to get the vector, so 5 is the first component. When we divide by 5, we're going to get 1. And minus 3 is the second component. We divide by 5, we're going to get minus 3/5. So where is it on the graph? Well, here is the displacement vector from here to here, but the actual velocity vector would be 1/5 of that. So it's from here, go over 1 and down minus 3/5. So there would be a velocity vector that describes the average velocity of the particle in this interval. So for every unit of time, that is the average change in the position. Now, a very important example historically and conceptually is that of a projectile going through parabolic motion, like the trajectory of a cannonball. fired at an angle. So here we have a two-dimensional picture of space. So this is like the ground, and this is the height. And this is the trajectory of a cannonball. There's the cannonball there. It's on its way down. Now, Galileo taught us that this is a parabolic curve. It's a parabola. And fortunately, we know all about the graphs of parabolas and how to write them efficiently. We know that in terms of x and y, we can write them as a quadratic expression, y equals some quadratic in x. And if we set things up so that this parabola starting here at 0, 0, and also hits the x-axis at some future point, say 2c, then, well, first of all, we know that the axis of symmetry will be halfway between these 2 points. So that will be at the point C. That's where the top will be reached. And it also means that the equation of the parabola will have zeros at x equals 0 and at x equals 2c. So there will be a factor of x as well as 2c minus x. And I've written 2c minus x so that the coefficient of x here is negative. And the k is just a positive scalar that we're introducing to allow us to scale the parabola up and down in the vertical direction. So this is an example of the general equation of the parabola that has this shape. So how can we describe the trajectory of a particle on such a parabola? Well, Galileo also understood that, and as we've talked about before, he realized that if you just look at the horizontal component of the motion as the particle's going up, the horizontal motion is uniform. We're going uniformly in this direction. So that means that the relationship between the time and the x is a linear relationship. If we set our clock so that time t is 0, it starts when the cannonball is here at 0, at x equals 0, then we can actually sort of rescale the units of our time, because the units are whatever we want them to be, so that time and x are in this case coordinated, so that they're actually equal. So we can parameterize this by setting the x coordinate equal to t, because Galileo has told us that the x coordinate is going to be proceeding linearly as time goes on. So if x is t, then y is just given by this expression, k times t times 2c minus t. And this then gives a parameterization of the curve. So for every value of t, we could plug that in here and we would get a point on the curve from t equals 0 all the way up to t equals 2c. All right, so we're in a position now to analyze velocities here. And I remind you that in an interval between a value of t, say t, and another value u, okay, in that interval, the formula for the velocity is it's the change in p, there's p, over the change in t. So we're going from t equals t to t equals u. And so the change in p is going to be p of u minus p of t, while the change in t is just u minus t. Now these are actual points that we know exactly how they look like. So here is p of u comma k u 2c minus u. And here is p of t comma k t times 2c minus t. And we have to divide all of that by u minus t. Now, we've seen this kind of thing before when we're talking about tangents, and a similar kind of thing happens here. If you think about the first coordinate here will be obviously u minus t. When we cancel with the u minus t, we're going to get 1 clearly. If we take the other component, the y component, we take this thing here and this one here and take the difference, well, there'll be a k factor. And if you write it out, you will see that there's also another u minus t factor, which doesn't surprise us because when t and u are equal, we expect the difference here to be 0. So there's going to be a u minus t factor in the second coordinates, the y coordinates, that will also cancel with the u minus t on the bottom. So after we've done all that cancellation, here is what remains. We first of all get a vector, because we have a difference of points, which is a vector. The first component is 1, and the second component is k times 2c minus t minus u. So that's an expression for the velocity between the particle at time t and time u. So this is the displacement vector, this vector here, but the actual velocity would be a scaling of that. We would have to divide that vector, that's the numerator, by the difference in time coordinate, u minus t, whatever that is. It's hard to say how much that is because we don't have a unit here. Okay? I haven't specified where the 1 is. You'd need to know where the 1 is here before you could see how big this actually is in terms of how much you'd have to scale that. But for example, if the 1 happened to be around here, then this difference would be about 2 or 3. You'd have to divide this by 2 or 3, so the actual velocity vector would be smaller, about like that. You can see that it would have to have x component 1. Maybe I'll write that down so that, so for example, if rather arbitrarily we chose our unit in the x direction to be 1 in that direction, then the velocity vector here is going to be this thing rescaled so that the x component is just 1. So it would be like this. That will be the velocity vector that we're computing over here. Okay, so now we are going to get to the notion of instantaneous velocity, which is a very subtle thing and has caused people difficulties for centuries, even from Aristotle's days. So Aristotle already knew that there was something difficult about the idea of how big the velocity of a particle is at a given time. So not in an interval, but actually at a particular point. So what's going on here? Well, let's look at it through the example that we've just looked at, the example of the parabolic motion of Galileo of a projectile. So here it is again, the same thing that before. And here's that same vector that we've computed before. There's p of t, there's p of u, and there's some velocity vector. In this case, our unit is 1 there. And so this thing has x direction length 1. Okay, so that's the velocity vector that's associated to the interval between t and u. So I've just copied the formula that we got there for the average velocity in the interval tu. And now we're going to think what happens as the point u approaches the point t. As these two values, t and u, for the time, start to merge together. So this point is fixed, but this point here is going to start moving towards this fixed point on the parabola. What's going to happen to this quantity? Well, actually, it's pretty easy to see what's going to happen, because if you just look at it and say, well, what happens as u approaches t, the dependence on u is very simple. There's only a u there with a minus sign. So as u approaches t, this term here is going to approach minus t. And the whole thing will have 2c minus 2t in this bracket. So we're going to get as a limiting value this instantaneous velocity v of t, which is 1, 2k times c minus t, where we've taken that 2, that's a common factor out of here after we've replaced u with t. This is then an expression that only depends on t. It doesn't depend on 2 points, it only depends on 1 point, and it is a limiting instantaneous velocity. It's the velocity of the particle exactly at the point t. Now you might think that it's a small thing, but it's not necessarily small. In this case here, it's going to have a bigger extent than this one here. As this point here moves over here, the average velocity is actually going to increase. Okay, anyway, so it'll look something like this. And it's important to realize that although I've framed this in terms of a limiting argument, in the same way that we looked at tangents earlier and saw that we could establish tangents in a purely algebraic way, we can do exactly the same thing here. We don't have to talk about a limiting phenomena. We can just talk in this algebraic setting about getting this formula from this one just by setting u equals to t. We don't have to take a limit where we are going through an infinite number of steps, getting closer and closer and closer. We can just do it all in one step. We just take u and replace it with t. Boom. You replace the u with t and you go immediately from here to here. So we can bypass the limiting argument that is natural from a physical point of view. This is a subtle business, and what we're doing here is really exploiting the fact that we know algebraically what this curve is. We know it's a parabola, and we have an algebraic expression both for the curve itself, and we have a parametric form for the equation. In real life, if you're a physicist or an astronomer and you're observing the motion of something, you do not have this at your disposal. You do not know beforehand an algebraic equation for the curve. What you can rather do is record positions of your moving particle at successive times. And you can try to make those successive times very close to one another. So you can decrease the amount of time between them. You can get a strobe camera and be taking lots of pictures per second. But nevertheless, there will necessarily be a finite element of time between two successive snapshots that you're taking. And when you calculate this instantaneous velocity, what you're really doing is not really calculating an instantaneous velocity exactly. You're calculating an average velocity over a very small period of time. That's what your odometer does, for example, in the car. It's just measuring separations between two very close adjacent time intervals. Getting at an instantaneous velocity from this physical point of view where you just have data is highly problematic and runs into philosophical questions about whether space is divisible, whether time is divisible, whether we're able to keep on getting smaller and smaller quantities. Actually, we know we can't do that because quantum mechanics gives us a lower limit to how far we can resolve things. Once we get down to about 10 to the minus 30 meters, quantum mechanical effects completely swamp everything, and we just cannot go further. So having said that, though, what we're doing here is mathematics, and we can get at least in this kind of situation, instantaneous velocities in this purely algebraic way, which is a very powerful aspect of this point of view. Right? We do not need the infinite process of taking more and more finer limits and sort of doing this to infinity until at the end of the rainbow we get a number. Rather, we just perform some straightforward algebraic substitution to finesse that whole issue. Considerations of position, velocity, and then acceleration were already topics of study in medieval Europe. There was a Merton school in Britain. There was an important mathematician named Oresme, and they made important contributions in understanding the basic relationships. And the story is really completed by an understanding that there's a second tier that we can go up. So from position to velocity is one tier, and then from velocity to acceleration is another. So just as velocity is the rate of change of position with respect to time, so acceleration is the rate of change of velocity with respect to time. And let's have a look at the definition because it's actually a little bit subtle. So we're talking about acceleration in an interval, t to u. It's a time interval. The rate of change is the change in velocity over the change in time. So there's the change in velocity. It's the velocity at the final point minus the velocity at the initial point. And notice that we do really need instantaneous velocities in order to make this happen. We need to have a notion of the velocity at the point u and the velocity at the point t. It's not enough to have velocities which are just average velocities over intervals. That's a challenge, of course, for physicists because it's hard for physicists to get at instantaneous velocities just through data, through observation. But anyway, that's the definition. Okay, let's see how it works out in our favorite example, a parabolic motion of Galileo, where you have a cannonball shot in the air, goes up and eventually lands further on down there. Here are two times, t equals t equals u. There's a velocity at time t. It's rather a big velocity because the cannon's just being shot out. Here a little bit later, it's getting close to the top of the trajectory, so it's starting to slow down. The velocity is, relatively speaking, smaller. In both cases, the velocities are, of course, tangential to the trajectory. So the acceleration in this time interval is the change in velocity over the change in time. And here are the velocities that we've just worked out. 1, 2k times c minus u minus 1, 2k times c minus t. When we take the difference, well, the 1's cancel. We're going to get 0 in our first component. And there will be a 2kc here and a 2kc, and they'll cancel. And then there'll be a 2k times minus u here, and then a plus 2kt. So that's 2k times minus u plus t. So when we cancel with the u minus t, we'll just get minus 2k. Now that's a very interesting result because it no longer has any dependence on either t or u. This is a constant acceleration independent of the time interval. So geometrically what's happening is that we're taking the difference between these two vectors, and to take the difference of two vectors geometrically, we like to put them together so that they're emanating from the same place. So if we take this vector u here and translate it down, about like that, well, both of their components will be 1, so they'll be lined up over each other. If we look at just like that, that should be lined up. Then they'll be lined up, and then the difference between them, so there's v sub u, there's v sub t, so the difference goes this way. Okay, so that there will be the difference v sub u minus v sub t. And now we have to get the acceleration, divide by the separation in times. Okay, so time is being equated with x here. We've arranged our coordinates that way. So if this is 1, then that's maybe a time of 2, let's say. And so we have to divide this vector by something approaching 2, and then the acceleration will be something like this. That will be the acceleration vector that we calculate for those 2 points. And the calculation shows that no matter which 2 points we choose, the acceleration is always the same. That's ultimately explained by Newton's laws and the fact that the gravitational force here is responsible for the acceleration, and that, at least close to the Earth's surface, the acceleration is constant. So the concepts that we've been talking about today mostly having to do with motion of particles, which are sort of the simplest things to talk about. But we should also be aware that physicists are also interested in the motion of more general objects. And that once the objects have more than just a zero-dimensional aspect, then the motion that they are able to support becomes more interesting. So for example, if you have a planar object, like a triangle, something like this, then you can consider that triangle moving. So here's a triangle. We can move the triangle. Well, we could just do a sort of simple thing like this. But we could also rotate it around as we're moving. Yeah. So this kind of motion here can be described as a combination of a center of mass motion. So if we know where the center of mass is of this thing, there's the center of mass, then we can describe this motion in terms of the actual point trajectory of the center of mass together with rotation of the object around its center of mass. So that's another sort of dimension of motion that ultimately we're going to be interested in. Another aspect of things that's quite important for the mathematical side of things, which we haven't talked about too much today, is that sort of a special case of what we're thinking is that sometimes we're interested not in points in mathematics, but in lines. So lines have a kind of dual existence to points. From many points of view, they're just as important as points are. So for example, we might describe curves not just by the trajectory of a point, but the trajectory of a line. An example of that is an asteroid. So that's the envelope of a moving segment touching the axes. So here's x and y axes as usual, and here's a segment. So if I lie this segment here, so it's now touching the y-axis, it's lying on the y-axis and it's touching the x-axis. So if I keep its two endpoints touching the two axes like this, then we can move like this, and it can actually keep on going down like this, and then up like this. And it will describe, well, there will be all these lines, but the lines will envelope a curve. A pleasant four-pointed star of some kind, that's called an asteroid. So it's described more by how a line is moving rather than how a point is moving. And that's typically something that we can do quite generally. We just take a line and start moving it around, and we can sort of see or have a look where nearby lines are intersecting. If we sort of draw those intersections, then we typically get a curve. So it gives us an alternate way of thinking about curves, and sometimes it's preferable to think about curves, or gives us an additional way of understanding curves by thinking about tangents. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.